Hi everyone, and thank you for joining me in this talk. My name is Yossi Luzon, and I'm from Afeka Tel-Aviv College of Engineering in Israel, the School of Industrial Engineering and Management. This study is part of my postdoctoral work where I collaborated with Professor Opher, Professor Oded Berman from Rotman School of Management at University of Toronto, and Professor Vedat Verter from Broad College of Business at Michigan State University. The title of the study is Strategic Capacity Deployment and Mutual Aid of an Emergency Vehicle Fleet. I'll start by representing Toronto Fire Services, which is TFS in short. It is an excellent example of a typical emergency vehicle fleet system. Next, I discuss the research problem and its objective. I'll present a model that we've formalized and found as a good fit. I conclude by demonstrating how the model can be applied to a specific district in downtown Toronto. Let's start with presenting Toronto Fire Services fleet. This is Toronto and its boundaries taken from Google Maps. The TFS is responsible for the entire city. Toronto Fire Services divide the city to 4 commands: north, south, east, and west. These commands are then divided to districts, and the districts are divided to stations. Here you can see the second layer of geographical classification of the city into districts. Each command is marked by 4 different colored shades: green, yellow, pink, and so on. These are the districts. The classification is numbered. For example, let's zoom into this shape at the top of the map, numbered by 241. The 2 indicates that it belongs to the East Command, Command 2. The 24 indicates the district, which is District 4 at the East Command, and the 1 is the station. The black dots in the figure indicate the specific placement of the stations. So this is station 241. The shapes around each station indicates its run area. This is the essential geographical jurisdiction which the station is responsible for. There are 3 main types of essential apparatuses in the TFS fleet: pumpers, aerials, and rescues. The following table provides their quantities in each district. For example, District 11 has 5 pumpers, 2 aerials, and 3 rescues. Each district includes a chief. The chief is responsible for managing an events scene, and it has a dedicated vehicle. So in total, we have 15 chiefs in Toronto. What you see here are all data records of events spread all over the city during 2016. We took these records and classified the activity of the vehicles in every layer: commands, districts, and stations. In the next slide, it was done in the district layer. As part of the operation of the fleet, it uses what we call mutual aid. Mutual aid between emergency stations refers to a long-term operational agreement among the stations regarding the extent of assistance across their jurisdictional regions, aka the run areas. We see 3 colored dots in the figure: red dots for District 11, purple for District 43, and pink ones for District 21. You can see the mutual aid phenomena in the way the dots of each district spread out of its region to different areas of the map. This means that stations are serving not only their own run areas, but other run areas as well. A typical timeline of an incident includes several timestamps as evolves as follows. It starts with the alarm, which is the time of the emergency call to the dispatcher. The next is the dispatch. Dispatch is the instant of a crew assignment to the event. From dispatch to en route is the length of time the staff is in preparation. And the arrival is when the crew declares its arrival to the scene. Control is used to announce that the event is under control, and clear is when the vehicle is ready to be dispatched to another event. In most cases, Once cleared, the vehicle head back to their stations. The following couple of tables show the involvement of vehicles in emergency events. The table on the left shows the participation distribution of chiefs. You can see that in over 95% of events that included a chief from 2011 to 2016, only a single chief was involved. Similarly, the table on the right shows that almost 80% of the events included the service of a single pumper. The situation is similar for other types of vehicles. This means that from a strategic perspective, events that include a single vehicle of a given type are the core activity of the fleet. So what is our model and how do we show it fits to the data and the real world? The objective is to minimize the number of vehicles required of a given type, their deployment, namely the spread of vehicles over the city area, and the extent of mutual aid allocation between stations. The trade-off is between the cost incurred for having too many active units in the fleet and the chances of having an emergency call wait for a unit to become available. What we know and assume is that the latter is much more costly. If you don't have a vehicle to dispatch and the event must wait, that means that you're in trouble, and that would be very expensive to the public. So if this assumption is valid, then it makes sense to assume that the TFS or any other mobile emergency platform for that matter should have a very high capacity relative to its demand. It means that the probability of having no available idle vehicles in the fleet should be very low if possible, and the budget allows it. It brings us to a known approximation that says that if rho, namely the load over the system, tends to zero, the capacity, that means that the capacity is high relative to the demand, then it is probable to assume that the MGZ system can be relaxed by the MG infinity one. It makes the analytical work easier since there is very little known about the MGC system as opposed to the MG infinity. We constructed a network of classes. One on the top of the figure, you can see the set of available vehicles of the fleet. The large arrow indicates the stream of demand as arriving emergency calls to the dispatcher. The dispatcher decides on the assignment of vehicles to events and for the rate of mutual aid as well. Each class indicated by the round shape and symbolizes a specific set of data. Exhibits an arc in the city of a stream of demand coming from run area I and being served by station J. This allows us to construct the cost function that considers the trade-off I have mentioned in the previous slide. What's important is to check whether this model captures the data and the actual dynamics of the system in the long run. What you see here is that it does. Consider this table on the left. The first column indicates the number of busy vehicles. The second one shows the proportion of time out of the years 2011 to 2016 that we had 0 busy chiefs, a single busy chief, 1 busy chief, 2 busy chiefs, and so on. You can see the nice fit to the one we obtained using the MIGI infinity on the next column, or the aggregated version to the entire city on the last column. These results are also depicted in the graph here on the right. It means that our model fits the data and we can use it to make strategic decisions. Let V be the cost incurred. So let's discuss the cost function that we built. Let V be the cost incurred for holding an idle vehicle in the fleet and having it ready to be dispatched. And U be the cost for the delay in serving an emergency event, both per unit of time. So we have V times the expected number of available vehicles in the fleet plus U times the expected number of queued events or calls that are waiting for service. And this is the actual expression for the cost function, which is the result of the MIGI infinity queuing model that I presented. I won't get into too many details about the total model that we call EVF, the Emergency Vehicle Fleet Model, because we're short in time, but this is the overall model. But I would say just that apart from finding the optimal fleet size, the deployment and mutual aid, it also accounts for response time. The response time is the time it takes the first apparatus arrive at the scene, which is a crucial component in any emergency vehicle fleet operation. You can see the response time according to this constraint here, that constraint it to the requirements of the authorities. Let's see an application of the model. We present that for a single district, District 31, which is in downtown Toronto, and is actually the place where I used to live when I was in my postdoc at U of T. So this is District 31. It has 5 stations, as you can see. You can also see very clearly that the stations are not necessarily placed at the center of their run areas. For example, here you see that these 2 stations are placed pretty close to the boundaries between these 2 run areas. What I'm presenting in the following slide was done for pumpers in this district. These tables show the basic input of the model, which is the expected service time when run area I is served by station J, given as ESIJ. The demand rates originated from each run area are given in the right column. And the lower table shows the corresponding mean response times, all taken from the real data that we had. The following table shows the current situation of the district. The rows are the run areas and the columns are the serving stations. We denote the ratio of mutual aid when run area I is served by an external station J as alpha ij. For example, run area 1 was served by its own station for 80.55% of the time and had mutual aid from station 2, which belongs to run area 2, 13.17% of the time. At the bottom, you can find the load applied over each station. In these tables, you can actually see our results obtained by our model. We present 7 cases of different cost ratios of V and U. The tables have 3 parts as expected. 1, the optimal fleet size. 2, the vehicle's deployment to stations. And 3, the optimal mutual rate allocation. It shows that as the cost of delay in service response increases from 1 to 100 in the first case to 1 to 10 million in the last case, then the optimal policy in terms of mutual aid is to avoid it, as you can see by following the bolded numbers in the diagonals of the tables. And sorry, that the numbers of vehicles should increase. You can see that Z increases. So Z here is 4, 5, 5, 4, and here it's 5 and turns to 6 in this ratio from 1 to 10 million. An interesting case is case 4, where the model finds that the optimal solution is having 4 vehicles instead of 5, but at the expense of increasing the load on station 2. You see that the load as compared to other stations is pretty high. Also, it's interesting to see that it sets only 4 vehicles when it actually means that we need to cancel station 4. Note that that observing the row lines in each table raises the question of fairness and whether the results are balanced in terms of the load spread over the stations. This brings us to the last slide, which shows that this last table shows that by using our model, you can also find the optimal load balanced solution for the system. The model finds a solution that applies a similar load over all stations in the district. Thank you very much for listening and have a great conference.